Listen. What do you hear? The song of 12,000 horsepower in action. Thousands of precision parts operating in flashing unison, obedient to the control of the skilled pilot and crew. Yet it takes a nightmarish panel of sensitive and complicated instruments and controls to adjust the power output for changing loads, speeds, and conditions in flight. Listen again. What do you hear? The familiar sound of a fine motor car engine. More than 100 horsepower, responsive to the driver's lightest touch on the accelerator. Yet this fine engine must be constantly controlled all the time it's in operation to keep its power in balance with changing requirements. Again, what do you hear? The purr of an electric generator. As electrical power loads vary, as conditions vary, throughout the minutes, hours, days, weeks, and months, so must the power be regulated by watchful operators to keep the generator turning at constant speed. What do you hear? You guessed it. The beating of a human heart. One of the most amazing machines on Earth. The normal human pulse is between 70 and 80 beats per minute. Yet this rhythm varies every time we move or change position. Like this when we are resting. Like this when we are running or at play. And changing too with our emotions when we are happy, angry, or frightened. Listen. What do you hear now? That's right, the ticking of a watch. An accurate watch ticks 5 times each second. Like the engines of airplane and motor car, like the generator, like the human heart, your watch is a power plant that must operate unfailingly under an infinite variety of conditions. Yet, unlike our heartbeat, the beat of this tiny power plant must never vary. Unlike the giant generator, it has no tons of concrete on which to rest solid, level, and safe from vibrations which might affect its accuracy. There are no watchful attendants, no careful drivers, no skilled pilots, no banks of instruments and controls to regulate its speed and guard its accuracy. What controls the ticking of a watch? Inside, we find a beautifully poised and balanced mechanism of springs and gears, pinions and bearings. And this entire mechanism must be confined to a very small space. Still, it must run at a constant speed. Never more, never less, with an accuracy that approaches perfection. To understand what goes on inside a watch, let's make a simple device that will keep time. We'll use a garden hose. First, we'll place a little water wheel and dial in the center. When water passes through, it will turn the wheel and make the hand on the dial move. Now we'll attach the hose to a faucet. The faucet is our source of power. The hose conducts the water, our power in this case, past the dial to the nozzle. The nozzle controls the flow of power. By turning the nozzle, we can allow just a little water to flow through the hose, and the hand on the dial will turn slowly. By opening the nozzle wider, we allow a heavy stream of water to flow through the hose, and the hand on the dial turns faster. If our source of power, the water pressure, remained constant, and if we could adjust the nozzle carefully enough, we would have a timepiece that would keep accurate time. Here, in a greatly simplified form, we have the 4 elements needed in every timepiece. A source of energy or power, a means of transmitting power, a dial to record the flow of power, and a way to control the power. Now let's see what these four elements are like in our watch. First, we'll take our watch apart, like this. We'll begin with this part, the mainspring and barrel assembly. And so we can see everything that goes on inside, let's use giant parts to make a watch model. This is the mainspring, and it lives inside the mainspring barrel. The mainspring is the power plant of the watch, the source of power, like the faucet in our water clock. By winding the spring, we can store up energy. Here is a winding stem with gears and a click to keep the spring from unwinding. And here is the unit that controls the flow of power, like the nozzle on our hose. It is called the balance wheel and hairspring assembly. It consists of the balance wheel, hairspring, balance staff or axle. Fastened to the balance staff is a part called a roller. To the roller is attached an upright jewel pin. Let's see how these work together. A push on the jewel pin will start the balance wheel moving, and more pushes will keep it moving. To do this job of pushing, we need this odd anchor-shaped lever called a pallet. It can be mounted so that when we move the pallet back and forth, we can apply a series of impulses to the jewel pin to keep the balance wheel in motion. Now to the pallet crossarm, we add a pallet jewel, shaped like this. Here is a wheel called an escape wheel, with teeth on it so shaped that they will push the pallet jewel and jog the balance wheel into motion. Now we'll use the energy stored up in our mainspring to drive the escape wheel. As the mainspring uncoils, it causes the barrel to rotate with it. That didn't last long, did it? Let's try it again. Once things get started, there's nothing to stop them. What we need now is a way of holding the power in check, releasing it a little at a time just when it's needed. Another pallet jewel at the other end of the pallet crossarm will do the trick. Just as the first pallet jewel gets a push from the escape wheel, the second pallet jewel locks against another tooth of the escape wheel to hold the power of the mainspring in check. But the balance wheel keeps swinging, and the jewel pin moves the fork end of the pallet until the escape wheel is again unlocked. But when we connect the mainspring directly to the escape wheel, the power is soon exhausted. In an actual watch, it would last only a few seconds. What we need is a way to stretch the power so it will last for more than a day. In our water clock, we used a hose to transmit power from the faucet to the nozzle. We also need a way to transmit power here. So let's add a system of gears and wheels. We'll stretch them out in a line instead of in their usual closely confined location in a watch. Look at the gears a moment and see what they do. First, a small partial turning of the mainspring barrel drives the center wheel a complete revolution. A partial revolution of the center wheel drives the third wheel a complete revolution. and this in turn drives the fourth wheel much further. As a result, a few turns of the mainspring barrel, driven by the mainspring, will drive the escape wheel many, many revolutions, enough to last a full day and longer. What we have now is a complete model watch train. Through the gears, the mainspring drives the escape wheel. The escape wheel teeth push first on one pallet jewel and then the other. The pallet fork nudges the jewel pin on the balance wheel to keep it moving. The swinging balance wheel on its return trip moves the pallet fork. This unlocks the escape wheel to release a little more energy from the mainspring. Back and forth, the balance wheel swings, controlled by its small coiled spring, the hairspring, in perfect rhythm. Each swing unlocks the escape wheel so it can give an extra push to a pallet jewel, and this is passed on to the balance wheel assembly to keep the watch ticking far more steadily than any beating heart. All we have to do now to measure time is count the ticks. But this would be a tedious job and not very practical. Just as we needed a dial on our water clock, here too we need a method for recording the flow of power. So to the shaft of this gear or wheel, we add an indicating hand to measure seconds. As the gear train of a watch moves far enough to make 5 ticks of the escapement, the second hand moves 1 graduation on its dial. To count the minutes, we can attach a dial and fasten a pointer to this gear wheel, which is just the right size so that it turns 1 complete revolution while the second hand makes 60 revolutions. And to count the hours, we can have another pointer geared just so, to move 1 complete revolution every 12 hours. The second hand makes a complete revolution and the minute hand moves 1 graduation, and when the minute hand makes a complete revolution, an hour has passed. Now we can tell what time it is. But a gear train all strung out like this is a long way from an actual watch. Let's let our model do a bit of rearranging all by itself. Now we know what time it is and how and why we know. A fine watch itself is, of course, a compact precision mechanism with parts miraculously small and fashioned by craftsmen with incredible accuracy. But the basic principles are those we have just seen, frequently applied on a scale almost microscopic to produce the world's most accurate, portable measuring instrument. In a truly fine watch, there are many things which make possible the accurate control and release of power. Jewels, for example. Many people correctly believe jewels increase the value of a watch. They increase the value all right, but not by being ornamental. Jewels are in a watch strictly for business. They add to the value only when correctly placed and used. They are the bearings which lessen friction, increase the regularity of the running, and greatly extend a watch's life of dependable service. Harder than the finest steel, these tiny surfaces are finished so smoothly they reflect images like a camera lens. And working with oil, it takes a drop no larger than a pinhead for the entire watch. There is almost no friction. If any single part of a watch can be called more important, it's the hairspring. It absorbs and gives out an equal amount of force with each beat or swing at regular intervals. In a fine watch, the hairspring has uniform thickness throughout its whole length, is polished to a mirror-like finish, and made of metal relatively unaffected by magnetism or changes in temperature. It can be apparently distorted, but it always returns to perfect shape. Hairsprings are overcoiled, like we see here, to allow the spring to breathe evenly. Were this not done, the spring would coil and uncoil unevenly, fluff out on one side, and interfere with the accuracy of the watch. Because a watch is required to run in any position, to be accurate, the balance wheel must be perfectly balanced in any position. This is done by poising. The wheel is poised when there is no effect of the pull of gravity reflected in its action on the knife-like edges of the instrument which checks it. With perfect poising, and with the hairspring centered on the balance wheel, it runs accurately in any position all the time. And it's the same with all the parts. The tiny screws, scarcely larger than a speck of dust. The exceedingly small shafts. The precisely made gears and pinions. The sturdy nickel-silver plates and bridges. Every part is made with utmost precision. Precision which approaches perfection. When we look at the almost invisible parts, understand what they are required to do, realize the uncanny skill needed to make a fine watch, we can easily understand why it is a masterpiece of precision and accuracy. Here is a truly wonderful mechanism. With it, you can accurately measure the passing of time and record that passing for your use and convenience. But this mighty little servant is a creation of beauty, too. A precious possession to be worn with pride and confidence every day, every week, every month, year after year. Listen. What do you hear? It's the ticking of a fine watch. Wherever you go, whatever you do, America's fine watch ticks steadily, accurately on. 5 ticks every second.